Good morning. My name is Sarah Parker, and I'm presenting my final project for model analysis. For this project, I decided to evaluate variance and do a comparative study of dimensionality reduction techniques for causal inference. So the problem is that dimensionality reduction is routinely applied as a neutral pre-processing step in causal inference pipelines. However, the discarded covariate directions may be exactly what's required for a valid causal adjustment. And a biased ATE estimate may influence policy decisions in healthcare, education, or economics because there's no obvious signal that something has gone wrong from the analysis. Where PCA maximizes variance, it does not, it's rather agnostic to causal structure. And autoencoders minimize reconstruction loss, but neither guarantees preserving confounders that may greatly influence a causal adjustment. So my key question is, does dimensionality reduction method choice introduce bias into a causal effect estimate? Some questions that I sought to answer were, does PCA discard the low variance features that are high impact confounders? Secondly, does a supervised compression, such as an LDA, preserve the causal structure better than an unsupervised method? And three, are some causal estimators just simply more robust than others to the representation quality? So the way I chose to try to address these three questions is through a systematic 4x3 experimental design on the IHDP benchmark. And the IHDP benchmark data set is the Infant Health and Development Program. There were 747 patients in this program, and they were low birth weight premature infants that received highly intensive childcare. The ground truth average treatment effect for this was 4.016 IQ points. So with this data set, there were 25 covariates. 6 of them were continuous, such as head circumference, gestational age, and then you had more binary, such as maternal education status and socioeconomic status, things of that nature. This was not a randomized treatment data set because the infants were specifically chosen based off of characteristics. There is about a 1-to-4 imbalance in that data set. So with our design, we chose 4 representations across 3 estimators to get 12 cells. Additionally, I did a PCA dimensionality sweep to assess for that. Our primary metric is our absolute ATE bias. So we compared the ATE from our estimators to the ground truth ATE of 4.016 IQ points. Secondarily, we looked at the precision and estimation of heterogeneous effects, and that measures individual treatment effects, and the mean standardized mean difference. So we have our 4 representations, which is our raw data set that has the full 25 dimensions. And then our 3, our PCA, LDA hybrid, and an autoencoder that are all reduced to 5 dimensions. We applied our 3 estimators to each of those representations using propensity score matching, a backdoor adjustment via OLS, and then a causal forest with a double machine learning to be exceptionally robust. And then our evaluation metrics as discussed previously. So with our PCA, this is a linear projection that maximizes the reconstructed variance. For our top 5 eigenvectors, we retained 41.1% variance. That's not super great. Ideally, you would like to have more variance retained. But it does work, and it's appropriate. And this is an unsupervised method. Our LDA hybrid is 1 supervised LDA access and then 4 PCA components. So this maximizes the treatment group separability on dimension 1. It's a semi-supervised method. Our autoencoder is an unsupervised method, and we use nonlinear bottleneck mapping via a neural network. You can see the architecture below, and we ran it over 250 epochs using an atom optimizer. Now, our mean SMD is actually very close to each other. Now, our baseline SMD was 0.182. And so the closest that we got is our PCA at 0.226. So for our estimators, the PCM is a propensity score matching, and it estimates via logistic regression and then matches each treated unit to its nearest control. The key property is that it uses the covariate space only through a scalar propensity score summary. Our backdoor adjustment is via the OLS, and it fits the linear model. The ATE estimate is the coefficient on the treatment indicator. And the key property for this is that it models the outcome surface directly and absorbs the representation-induced imbalance. Third is our causal forest double machine learning. This is a random forest nuisance model, and then it takes the residualized ATE and computes it. The key property is that it's doubly robust. It's consistent if either the outcome or the propensity model is correct. These were the results that we got from running our representations and our estimators. So the best was actually our PCA combined with our propensity score matching. It gave us an ATE of 3.996, which was a bias of only negative 0.020. If you'll remember, our true ATE is 4.016. And so what's important to realize is that all four representations recover our ATE within 0.55 IQ points of our true ATE when it's paired within the right estimator. So this is actually very significant because no estimator and representation failed singly. In general, the causal forest did better with our raw covariate space, our LDA, and our autoencoder. And we'll talk about that more in just a little bit. So the bias was not determined by the representation alone. It's more determined by the interaction between the representation and the estimator. So it's very important to choose the right estimator to go with the representation. Our propensity score matching was highly sensitive, and the bias range was 27 times wider than the OLS. You can see it was 0.02 all the way up to 0.54. And so the scalar propensity is more vulnerable to the representation distortion of that 4:1. The OLS is our backdoor adjustment, and it's very robust. The bias on it was much narrower. It's 0.087 to 0.173. And our causal forest was the most robust. It was 0.028 to 0.274. So this flexible random forest model worked very well with our imperfect covariate space and our doubly robust structure. When we did the PCA dimensionality sweep, you can see that the red line represents the propensity score matching, where the blue line is our backdoor adjustment. And our propensity score matching is very non-monotonic. There is no convergence towards zero as K increases. You can see that it dips very significantly at K 3 to 5 and then increases again. The OLS stays below 0.173 across all the K values. When looking at K3 through 5, it's important to note that this is coincidental. It's not a general property that it went down to 0.0. And that's just because it's more likely that the high variance features of what impacted the data set happen to be there. So our conclusion is that there really was no catastrophic failure. All the representations recovered the true ATE within 0.055 IQ points when paired with the appropriate estimator. The PSM is the most sensitive. The bias range was very large. And that really is just the PCA success was coincidental, that near zero bias at K5, because the top components just aligned with the propensity relevant subspace in our data set. Co-selection really matters. Our autoencoder plus our causal forest gave us only a 0.028 bias. But if you use that same autoencoder and a PSM, then the bias increases pretty significantly. So the estimator choice is critical. The practical implications is that I would prefer using a backdoor adjustment or the DML-based estimator when you're applying compression upstream. The propensity score matching really should only be used with caution after compression and never with representations that maximize that treatment group separation. So that concludes my final project on causal estimators and how it impacts variance. Thank you.